Okay, let's start. Hi everybody, welcome back. Please feel free to turn on your videos and let me make a few announcements. So, as usual, the third homework is due right now. The next one is going to be due next Friday. And after that, the midterm is going to be in 2 weeks from now, which is, I think, May 7th, if I'm correct. Yes, I'm going to send an email about the midterm and all the policies and stuff. But yeah, so there's going to be no homework due after homework 4. There's going to be no homework 5. And and the midterm is going to cover the first 5 weeks of our classes. So yeah, I'm gonna send a pretty detailed email about the midterm. So yeah, any questions on this stuff? Okay. Yeah, and the midterm is going to be basically just another homework, but sort of more nervous, I guess. Yeah, you're going to have 24 hours and just all the usual pandemic stuff. So yeah, anyways, let me remind you what we started doing last time, which was generating functions. So there is ordinary generating functions. Right? If you give me a sequence, then I can just write it down as a formal sum like this, or I can write it down as an exponential generating function, depending on which is more convenient. X to the n over n factorial. So these are just treated as formal sums. And last time I discussed how to multiply and divide and add such formal power series. Right? So these are formal power series. And yeah, today I want to try to actually compute some stuff we either couldn't compute before, or it was hard to do combinatorially. I'm just going to try to do it by manipulating functions as I would do in calculus. So before I do that, let me try to introduce a few more operations. So first of all, I'm going to use convenient notation for the coefficients. Sometimes I have a generated function and I want to extract one particular coefficient f sub n. So the notation for that is if f of x is the sum fn x to the n, then denote bracket x to the n f of x to be the coefficient of x to the n in f of x. Right, so it's pretty standard notation. And yeah, so if for exponential generated functions is going to be convenient. So if it's f sub n x to the n over n factorial, then I'm going to denote these coefficients f sub n to be consistent as x to the n. So I want the coefficient of x to the n over n factorial. That's going to be f sub n. Right. So just notation for extracting these coefficients, and the most important one is going to be the constant term. So constant term is going to be denoted either x to the 0 f of x, or also f of 0. That's just f0. Yeah. So okay. And now let me try to introduce a couple of more operations on generated functions. Right. So one operation you can do is, as you learn in calculus, you can take derivatives. So operations on generating functions. Right, derivative is something you learn that it's sort of, you have to change x by a little bit and then measure how much the function changes. So I'm not going to do that. I'm just going to do it formally because the series may not converge. Right? So I have to, and it's very easy to define formally. So for f of x, the sum. So if you have a formal power series like this, the derivative f prime of x is just by definition, I differentiate term by term. N times f sub n, well, I have to take, n goes now from 1 up to infinity, x to the n minus 1. So that's a new power series where each nth term got multiplied by n. And again, this guy the original guy may not have been differentiable in the usual sense, and this series may not converge, but as formal power series, it's always well defined. And yeah, it satisfies all the usual rules. Satisfies all the usual rules for differentiation, right? So yeah, you can take the derivative of the sum is the sum of derivatives, and similarly for product, just everything you're used to. So formally I would have to prove each of these rules, and that boils down to some sort of combinatorial arguments with like formal power series. All right, but f over g prime, hopefully I get this one correctly, g prime over g squared. So this last one is if, assuming g is invertible as a formal power series. Right, so remember we had this double bracket c double bracket x, that's the I guess the ring or the set of formal power series. So g has to be invertible for this formula to make sense. And so the proof, I'm gonna just say exercise. But yeah, feel free to use these rules for all formal power series. Yeah, and there's also integration. Integration is, I'm not gonna use it, I think. So, but in general, integration is similar. You just integrate each term in your sum, and then you add a constant or whatever. So yeah, that's one thing you can do with formal power series is differentiate, and so that's useful sometimes. When you have n appearing in your coefficients, that may be a sign that you're dealing with the derivative of some function. Now, yeah, let me also mention another nice operation. So I'm going to state it as binomial theorem, right? That's another fact you learn in calculus. Binomial theorem. We already discussed it with integer exponent, but you can also take 1 plus x to the alpha. Right? So you can take alpha to be arbitrary. For alpha in C. Right, or I mean, it can be real or it can be even complex. Yeah, let me write real because I don't think we're going to use it for complex numbers anywhere. But for real numbers, like maybe 1/2 to get the square root, you get the sum for n bigger than 0, alpha choose n times x to the n, and I have to define the binomial coefficient for. So alpha choose n, just by definition, it's the following factorial, alpha minus 1, all the way up to alpha minus n plus 1 divided by n factorial. Is that familiar, or is it completely, you've never seen this statement before in your life? Okay, yeah, I mean, if you, in calculus, if you want to like expand 1 plus x, the square root of 1 plus x, like 1 plus 1/2 x plus etc. If you just write down the Taylor series, then these coefficients are gonna be exactly given by these sort of generalized binomial coefficients. When alpha is an integer, by the way, what happens when alpha is an integer? When alpha is an integer, this sum becomes finite, because if alpha is an integer, you multiply, right, when n is large, one of these terms is going to be 0. Is this related to the gamma function? I mean, I don't think it's direct. I mean, maybe there is like everything is related, but I don't see. Right, gamma function is the sort of a generalization of the factorial to arbitrary real numbers, and yeah, I have to think about it. Maybe this can be written as a ratio of gamma functions. Yeah, that's a good question. Right off the top of my head, I'm not sure, but it may be related. Any other questions? Which, by the way, I mean, for us, right, we don't really talk about Taylor expansions and stuff, so we are inspired by them, but not. So the point I'm trying to make is that this is the definition. The definition of formal power series 1 plus x to the alpha. Right. So it is inspired by calculus, but then because the definition is sort of inspired by calculus, it satisfies all the usual rules of algebra. So satisfies all usual rules. Like, for instance, you're allowed to take 1 plus x to the alpha times 1 plus x to the beta, 1 plus x alpha plus beta, or you can take 1 plus x. I guess you can raise it to the alpha and then to the beta, 1 plus x alpha times beta, etc. So, and again, each of these can be deduced by some manipulation with these generalized binomial coefficients. Yeah. So yeah, I mean, this is I think this should be just gamma function of alpha divided by gamma function of alpha minus n times gamma of n, which just by definition gamma of n, this is n factorial, and the ratio of these should be just the numerator. So it should be, if I'm, yeah, I think this can be expressed using the gamma function. But I mean, this is in general, gamma function is much harder than you just multiply a bunch of explicit numbers. For the gamma function, usually it's harder to deal. Yeah. Okay. So these are the basic operations, and later I'm going to discuss which. Later I'm going to tell you that instead of x, you can basically put any other any formal power series without a constant term. But for that, we have to discuss more general infinite sums where each term is itself a power series. So yeah, I want to do this rigorously, and I'm going to do this later. But for now, even 1 plus x is already good enough for us. So yeah, now let me try to compute some nice examples. So finally, okay, yeah, I have some time to. Okay, here is the first example. Yeah, that's going to be the, because for generating functions you have to just do a lot of exercises, and that's where you get all the experience and kind of really feel what the exponential generating function is for and what the ordinary one is for. So here's an example. I want to take the formal power series, so which is just going to be a sequence. I want to take the sequence 1, 2, 3, 4, 5, etc. 1 plus 2x plus 3x squared plus etc. So for the rest of this lecture, I'm just going to take some nice sequences and then see what I can say about the generating function. Okay, so question: how do we compute this? How do we find some kind of closed formula for a generating function like this? Oh, okay, interesting. So I multiply x times f of x minus f of x. Is that so? You would just multiply by x minus 1. Okay, so I guess, yeah, you're saying I'm going to get just the sum of n greater than or equal to 0, and each coefficient is going to be n plus 1 minus n, x to the n. Is that, or am I going to get an extra? Yeah, I think that's what's going to happen, right? So 1 over 1 minus x. Alternative is the derivative of 1 over 1 minus x. Okay, yeah, that's great, right? So there's two ways to. So yeah, right. The first way, if you just divide by. Wait, why is the sign different? Oh, okay. Sorry. To get this expression, you have to negate the expression on the left, right? Because n plus 1 times x to the n is the coefficient of f of x. So you have to take f of x minus x times f of x, which gives you minus n x to the. No, wait, what? Okay, algebra is hard. No, I think this is correct. Yeah, I think this is good. Anyways, the point is that f of x is just equal to 1 over 1 minus x squared. And yeah, another way, alternatively, if you just look at the formula here, you see that you have n plus 1 times x to the n. So that's the derivative of is the derivative of the sum n greater than or equal to 0, x to the n plus 1. Yeah. So and this sum is. Wait. well, I can, if I take the derivative, then I can add any constants to it. So I can even say that it's 1 plus this sum, which is 1 over 1 minus x. Right. So, or you can say whatever, 1 minus x minus 1, right? Because there is no constant term on the left. So now I'm allowed to take the derivative. Thus, f of x is 1 over 1 minus x squared, which is just the derivative of this guy. And okay, so that was a warm-up example, I guess. But yeah, so let's try something a little bit more tricky. So the next example is going to be, by the way, any questions? Any questions so far? Because it's going to get harder. Okay, no questions. The next example is going to be everyone's favorite numbers, the Fibonacci numbers. Which is, by definition, they're defined by a recurrence relation. And in the homework, you're going to get a few more recurrence relation problems. So yeah, recurrence relations are very can be easily tackled using generating functions. So in this particular case, generating functions are very, very useful. an minus 1 plus a n minus 2. So you can define the formula, you can consider the, let's say, ordinary generating function for the Fibonacci numbers. Okay, how do I find a closed formula for the generating function? Oh, okay. Okay. All right, so indeed, let's try f of x is a0 plus a1x plus a2 x squared plus a3 x cubed plus etc. And then if you write x times f of x, you're going to get a0 x plus a2 x plus a1 x squared plus a2 x cubed, etc. And then if you take x squared f of x, then you get a0 x squared plus a1 x cubed plus etc. So if you now subtract the sum of these two from f of x minus x f of x minus x squared f of x, then you get, let's see, a0 plus a0 and a1 are equal to 1, so you don't get any of the x's. And then a2 is equal to a1 plus a0, and a3 is equal to a2 plus a1, and etc. So you just get a1, which is equal to 1. And now you can divide. Yeah, in the homework you're going to see that you can divide by 1 minus x squared, so that power series, well, this power series 1 minus x squared is invertible. So if you divide, you get the generating function for the Fibonacci numbers. And at this point, you may ask, like, why is it useful to, I mean, okay, whatever, we get some formula. like it's still hard to express this in like Taylor series. And a lot of times you can actually first find the generating function, and then you can find some nice formula for your numbers. So let me try to use this formula right now to actually say some nice statement about the Fibonacci numbers. So here's a question. Like, let's say I give you this generating function. How do you find how to find a formula for each coefficient? I mean, of course, you can kind of reverse engineer a recurrence relation, but is there any other thing you can do with the function like this to then expand it as a Taylor series easily? Each coefficient is the correct derivative divided by some factorial, so do that, but break it into partial fractions. Oh, nice. Okay. All right. So let's try partial fractions. Which, yeah, so this is something I haven't done in at least 8 years, I would say. But luckily, I have an expansion. Yeah, I have an expansion into partial fractions right on the left of my screen. So, but I mean, it's easy. You can factor the polynomial into linear factors. Right? It has like its roots are the golden ratio and its inverse. So okay, let tau be the golden ratio, 1 plus square root of 5 over 2, and let tau bar, which is the basically 1 over tau, is, well, I guess, negative 1 over tau. Negative 1 over tau is 1 minus square root of 5 over 2. So these are the roots of your denominator. And then you can, after some trial and error, you can even use the computer. Like, you can go to Wolfram Alpha and then just ask it to find a partial fraction decomposition. And what you get is 1 over x plus tau minus 1 over x plus tau bar. I think that's, yeah, after some computation, you get basically this form. I mean, it's very easy to check that these two polynomials these two rational functions are equal to each other. And now, indeed, I can, because each of them is basically 1 over a constant plus x, so I can represent each of these as some constant times 1 over 1 minus. Yeah, anyway, what I'm going to do is I'm going to use 1 over 1 minus alpha x is equal to the sum alpha x to the n. So I can use the formula for geometric progressions. And then I can say it like 1 over x plus tau is, I guess, 1 over tau times 1 over 1 plus 1 over tau x, or something like this. So alpha is equal to negative 1 over tau in this case, which is tau bar, I guess. Anyways, you can getting the coefficients of these rational functions is a very easy just geometric progressions exercise, and the result that you get out of it is the formula that many of you have probably seen before. So the answer, after you do all the calculations, is that the nth Fibonacci number is 1 over square root of 5 times tau to the n plus 1 minus tau bar to the n plus 1. So this is positive and this is a negative number, so the signs of the second term are going to alternate. So let me even write it, because if this is the first time you see this formula, you should be going crazy right now, because so 1 plus square root of 5 over 2 to the n plus 1 minus 1 minus square root of 5 over 2 to the n plus 1. And yeah, it can also be deduced using like linear algebra and eigenvalues, which is roughly equivalent to what we did here. But the bottom line is that on the left, I have Fibonacci numbers. Right? They're integers. They have some combinatorial interpretation. And on the, that's on the left. And on the right, I have some expression in terms of irrational numbers, which cannot quite be simplified any further. So if you have a calculator, you can compute, and you indeed get an integer for each n, even though you have to do computations with irrational numbers. And which, by the way, this has some, if you were a computer scientist, like some of you probably are, you would argue then that, okay, to compute the right-hand side, I would have to compute many digits of square root of 5. So algorithmically, it's not very clear that the formula on the right is more efficient than just using the recurrence relation. But yeah, mathematically, I think it's a very nice fact, which we just got from very simple manipulations with generating functions. Matrix exponentiation. Okay, yes. If you know about matrices, then you have seen this before, and yeah, I mean, but all right, let's try another one. By the way, any questions before I try the next favorite sequence? This was much more fun than matrices, though. Okay, thank you. Yeah, this is more fun for me as well. But I mean, matrices are also fun if you do it the right way. All right, no other questions? Yeah, let me try to do another example, which is Catalan numbers. So as a reminder, it's been a few lectures since we studied Catalan numbers. So you take, there is a formula for them, right? Which is, there was some very involved proof I did with kind of explaining why this formula counts. This is the number of north-east lattice paths, which stay above the diagonal and go from 0, 0 to n, n. Right? And yeah, I even have a table. Let me write the table down. So n and cn, because I'm gonna 0, 1, 2, 3, 4, 5, 6, 7, 1, 1, 2, 5, 14, 42, 132, and 429, and etc. So, or also the number of triangulations, and yeah, so what can we do? We already have a nice formula here, and we have this interpretation here. So what I'm going to try to do right now is I'm going to forget this formula. And instead, I'm going to use the lattice path interpretation to deduce the formula from the lattice paths without any bijections, just using generating functions. So, okay, let me define, again, today I'm only doing the ordinary generating functions. F of x, the sum, n greater or equal to 0, cn x to the n. And again, what I'm going to ask is, what is a closed formula for f of x? which, yeah, I'm not asking you to figure this out on the spot, but it's a nice exercise to try to imagine, like what is the answer going to be? Is it going to look like exponent of some stuff, or maybe the sine of x or whatever? It's not really easy to guess what the answer is going to be. But to get the answer, what I'm going to do is I'm going to compute f of x, what I'm going to do is I'm going to find a recurrence for the Catalan numbers. Because previously we did like bijections, but the Catalan numbers satisfy a nice recurrence. So here's the claim, I guess. All right, here's the claim. Claim is that the recurrence for Catalan numbers is a very simple statement. You just, the next one, the n plus first one, is the sum from 0 to n, ci times c n minus I. So here is the let's see if this works. So maybe I should compute C4. Well, let's start with C3. C3 is 5. It should be equal to, you just take sort of, you multiply the first by the last, plus the second times the second, plus the last by the first. So 1 times 2 plus 1 times 1 plus 2 times 1, which is 5. Or C4 is 14. So you get 5 times, well, okay, let's do left to right. 1 times 5 plus 1 times 2 plus 2 times 1 plus 5 times 1, which is 14. And C5 is, 42 is 1 times 14 plus 1 times 5 plus 2 times 2 plus 5 times 1 plus 14 times 1, which is, 42. So why is this true? Proof of the claim. All right, I have to, let's say I have some, let's say I have 0, 0, and then I draw the diagonal, n, comma n, and then I have some lattice path, maybe something like this. So, and I want to find a recurrence, which expresses the number of lattice paths in some sort of smaller lattice paths. And the way I'm going to do that, or maybe somebody can guess what I'm going to do. Passes through n, comma n minus I. Or, right, for n, comma n minus I, wait, n minus I, n minus I. I, n minus I. Oh, so you want the recurrence to kind of go according to which of these points it passes through. And actually, yeah, that's not the right guess, but it's close, right? So the right guess is to look at where it touches y minus x. Wait, y equals to x. Yeah, okay, right. That's the correct one. You just what you do is you let q be the, is it q or is it Oh, okay, I even have n plus, okay, let's have n plus 1 comma n plus 1, because it's going to be, in the recurrence, it's, in the recurrence here, on the left-hand side, you have n plus 1. So I have to take n plus 1, n plus 1. And let q be the first point on the y equals to x diagonal, where our path, well, on our path. Right, so, and q, I mean, of course there's 0, 0, but q has to be the next point after 0, 0. So this point right here is q. And then, so what you observe is that the first step is always north. The last step before q is always east, right? So these two steps are already determined, and then the path over here, it does not go below, so it may touch this this is y equals to x plus 1 diagonal, right? So the part from between these two steps stays above the line y equals to x plus 1. Does it make sense, or? Okay. No questions. All right, so can it touch y equals to x plus 1? Yes. So it can touch. Yeah, so I mean, it can. Maybe I should try to draw some. Yeah, it can go like this, for example, right? Because all we know is that the part between 0, 0 and q does not touch the diagonal at all. So it has to stay above this lifted diagonal. Why does it need to touch y equals to x? Why not n and n, e? Right, I mean, yeah, there is a special case. So yeah, let me just say that q is equal to, what is it, I plus 1, where I is between 0 and n. So in particular, if I is equal to n, then q is n plus 1, in which case our path just goes all the way north and then all the way east. So this is q equal to n plus 1, n plus 1. Yeah, in this case, still we know that the remaining part stays above this lifted diagonal. So we still get new information even if q is the last point, n plus 1 comma n plus 1. And yeah, so and then you just count. So if q is I plus 1 comma I plus 1, then there is ci choices for, well, maybe I should introduce some notation. Let's say this part is p, this red part is p1, this is p2. So c it has to stay above, I think. Okay, there's some discussion. All right. Yeah. So, I mean, the first step has to be up, because if it goes down, then it goes below the diagonal. So there is, the point is that there is Catalan many choices for the kind of the part of the path between the first step and the last step before Q, and there is Catalan many choices for the rest. So I choices for P1 and C n minus I choices for P2. And that's where you just sum over all I, and then that's where you get the recurrence. Yeah. So now I have this recurrence, right? Let me try to copy the recurrence. So now I'm going to try to convert this into an equation on the generating function. So how do I? This is slightly different from what we had before, right? It's not just it's a recurrence relation which involves all the previous values, and the idea is that you just multiply both sides by x to the n plus 1. Even just put x to the n plus 1 here and x to the n plus 1 here, right? Then you can write this as x to the I ci times x to the n minus I cn minus I times x is equal to n plus 1 cn plus 1. And then you just sum over all n. I have this equation, and what happens if I sum over all n? Well, the point is that basically I get, on the left I get, yeah, let me try to be careful here, because, okay, so what do I get on the left? I claim that it's f of x minus 1, because there is no constant term. If I sum over, if n is 0, then this is going to be x times c1. But yeah, on the right hand side, what I get is x times f of x squared. There is an extra x, but then the rest is I have just literally multiplied f of x by itself. So there's a product formula from the previous lecture. If I just apply the formula, I get f of x squared. Well, if I just expand f of x squared as a just using the same formula as for product of two polynomials, then I get this formula for the coefficients. So in particular, f of x, I get a quadratic equation on f of x. So I can solve my quadratic equation, even though, so what I'm going to do now is not quite rigorous. But as an inspiration, I can solve a quadratic equation, right? I can do that. So I can solve it for f of x. And what I get is a solution to my quadratic equation, which looks like this. F of x is equal to 1 plus or minus square root of 1 minus 4x over 2x. So let me be very clear. This is non-rigorous. You can't just, if you mindlessly manipulate generating functions, you get weird things. Like for example, here there is a plus minus, right? F of x is a well-defined formal power series, but on the right you have all of a sudden you have two solutions somehow. But let me, and as we discussed, x is not invertible as a formal power series. So the right-hand side, the point is that the right-hand side does not really make sense as a formal power series. And I guess I'm out of time, so in the pre-recorded lecture, I'm going to explain how to make it rigorous. So next lecture, I'm going to explain that, this approach can be made rigorous, and the rigorous solution, which still this intuition helps us to, the actual answer is going to be f of x is 1 minus 4x square root over 2x. I think that's the answer, which, if you stop and think about it, Catalan numbers count triangulations or lattice paths or whatever. You just ask a natural question: what is the generating function? And then you get this expression. That's the first time I saw it, it was pretty surprising to me. Yeah, and I'm going to explain this. And then you can use this expression to find the actual formula using the binomial coefficients. So that's it. If you have any questions, let me know. If not, I will see you all on Wednesday, and have a nice weekend. Thanks.